So here we're going to continue with our proof strategies. Now we're going to look at, so previously we looked at direct proofs where you have an implication and if P then Q, right? So now in this case, we have seen before that this is logically equivalent to not Q implies not P, right? Our contraposition, right? The contrapositive. Right, so as it turns out, well, if you want to prove a statement P implies Q, it is equivalent, since it is logically equivalent, to proving the contraposition, not Q and not P. All right, so let's go through some examples here, right? So let's say we were asked, prove that if 7x plus 5 is odd, then x is even. And again, when dealing this, we'll look at for all x that are integers, right? Element of z. Okay. All right. And again, for all x that are integers. Okay, so if P is the statement, right, that 7x plus 5 is odd, and then Q, x is even. So our goal here is to prove P implies Q, but I'm going to do it in a what's called an indirect way, right? Direct proof, we directly started with the hypothesis, and we went from there applying any definitions and algebra that we know. But here we're going to look at not Q implies not P. And in proving that proves the implication P implies Q, since they are logically equivalent statements. So proving one proves the other. All right, so here the statement is going to be if x is odd, right? That negates the even part, right? Then 7x plus 5 is even. Okay, so again, we'll start by defining let x be an odd number. So we can call it 2k plus 1, right? The form of any odd integer can be written like this. Okay, so moving along here. So then that means, all right, so let's look at the statement 7x plus 5. And now let's substitute our assumption here. And now distribute, we get 14k plus 7 plus 5, right? And then doing some algebra, 14k plus 12, right? And notice here, doing some factoring, 7k plus 6. All right, and now notice here, right, since 7k plus 6 is just some other integer, right? Since the integers are closed under multiplication and addition, and 2 times an integer is an even integer, so therefore 7x plus 5 is even. Okay. All right. So now let's take a look at, let's do one more example, also using contrapositive, but also introducing a different type of statement that we've seen before, but we haven't done any proofs involving a biconditional statement. So again, for all x, element of z, right? So for any integer, prove that five x minus 11 is even if and only if x is odd. Okay, now this is a biconditional. All right. Now, again, as mentioned before, right, it implies a much stronger connection than a conditional rather than an if-then statement, right? Because here, right, symbolically, if and only Q, right? So what that statement is saying, right, P implies Q, but also Q implies P, right? That's what that biconditional is telling me, that this is equivalent to that. All right, so when we do have a biconditional, we need to prove two directions, right? These are the two directions, right? So our biconditional proof is going to involve the first direction, right? P implies Q, and then the other direction, Q implies P. All right. Excuse me. Okay, now we're going to do both of those directions using the contrapositive. All right, so here first, our statement P is 5x minus 11 is even. Q, x is odd. All right, so our first direction, P implies Q. The contrapositive is not Q. Oops. Implies not P. Right, so in other words, we say if x is even, then 5x minus 11 is odd. All right. Okay. Okay. So here, okay. So x is even, then 5x minus 11 is odd. So we'll start with our proof. X is even, x can be written as 2k. So going with 5x minus 11, that's going to be equal to, doing some substitution, 2k minus 11, and we get 10k minus 11. So I want to write this in in the form that we're used to. So what I'm going to do here is I'm going to here I'm going to rewrite the 11 like this, minus 10 minus 1. And the reason for that is, as we can see here, so now I have an even integer subtracted by 1. All right, so again, that is the form of an odd integer, right? I know we say plus 1, but minus 1 has the same effect, right? Because if 2k is even, the number above it, next to it, after it, or before it, that one is odd. So we can see here, right, that therefore 5x minus 11 is odd. Now this does not complete our proof, right? Excuse me. Okay? So in this case, since it's a biconditional, we need to go the other direction as well, right? So we need to do Q implies P. And we'll take the contrapositive, so not P implies not Q. So the statement here is if 5x minus 11 is odd, then x is even. Okay, so we'll start again. Here we start with the fact that 5x minus 11 is odd. So I can write that as 2k plus 1. Okay, all right, so this is true, right? This is our hypothesis. We take that to be true. All right, and now let's look at how that affects, excuse me. Okay, so here we add 11 to both sides. And then we get 5x is equal to 2k plus 12. All right. Okay, and then here we have 5x is equal to 2k plus 12. All right. Alrighty then. And then here we have 5x is equal to 2 times k plus 6. All right. All right. And now we have here that this actually proves that x is even. All right. Excuse me. All right. So we have 5x is even, right? And as I think we've seen before here, right? If we have a product of numbers, right, as we've seen before, that A and B is even, then either A is even or B is even. 5, right, is not even, so that means that X must be even. So therefore, X is even. Okay. All right, and that concludes